Hello everyone and welcome to the lecture on the two-spin channel model. In the previous lectures we discussed briefly the motivation of staying behind the spintronics, and we discussed the basics of electric conductivity, and today finally we are coming to actually the spintronic. Before we will move on, let me say a few words about the types of electric transport. In the basics lecture last time, we were discussing so-called diffusive transport, in which electron moves with such multiple scattering events, like we have seen, for example, that movie demonstrating Rudin model. And here, the electron free path is much smaller than the length of the sample. Nevertheless, in electronics, we need to consider also other types of transport. First of all, so-called ballistic transport, which is similar somehow to the cannon, because when your electron is coming to the sample, its free path is much larger than the size of the sample, and it means that it just flies through. Of course, in order to have ballistic transport, you need either very good conductors with large lambda, or you need nanostructure, simply very small structures that the electron propagates the whole structure without scattering. In addition to these two, we will discuss in this course also tunneling transport. You know that electron position of electron is described in quantum physics with its wave function. And if you have such systems that there is a conductor from this side, there is a conductor from that side, and in between there is an insulator, then the function of this electron in this conductor decreases as one instance wave, so it decreases exponentially. There's a probability that the electron will show up at the other side of the tunneling contact is not zero, and therefore electron can tunnel through the contact. And this is named as a tunneling effect, and it's very important, for example, in tunneling magnetoresistance effect, which we'll discuss later. And the final type of transport is named hopping. So if you have localized states, so it's somehow similar to the tunneling, but here we have a localized state. There is a non-zero probability that electron will hop from one state to another. But this one we will not use in the course of spintronics advanced materials.
Good. And what is this two-spin channel model? What does it mean? Principally, it's very important. It's very simple, but very important because all our spintronics, which we'll discuss in the next lecture, is based on it. An idea is very simple. We just consider electrons, we split electrons into independent parts. Electrons we spin up and electrons we spin down. And then the main picture about two-spin channel model is shown here. Especially made it red, that is to increase its importance. And then everything what you want to describe in your system, when you take into account the spin of electron in addition to charge, that's the job of spintronics, you just describe in the form of two resistors which are connected in parallel. So that resistance, your total resistance of your material will be given by the resistance of this two, not sum by this resistance, but particularly like two resistors connected parallel. So for spins down and for spins up. Of course, it assumes, in order to be able to use this model, you assume two things. So first of all, you say that electrons at the Fermi levels that carry the current are split into different states, exhibiting different conduction properties. So you say that these resistors here have different resistance. Only in this sense it makes sense to split electrons into type. So we really have to create a situation when, depending if your electron has spin up or down, it, for example, scatters more or less, or it moves faster or slower. It changes its mobility. And second, what you need to assume is that there is no connection between here, that your electron does not change spin, and so-called spin flip scattering, and this we'll discuss in a minute. But having this assumption, then, as I said, the resistance of your material can be found in this word, in these terms, like simply two resistors. If to come to Sommerfeld model, what does it mean? It means very simple, that now when you will apply electric field, so this was your steady state without electric field, then you applied electric field in order to get electric conductivity, and you have different shift in Fermi surfaces. For spin up, like shown here, it will be, for example, blue, so smaller shift, and for spin down, for example, it will be a larger shift. Good. So coming back to the point, do we really have different resistivities for spin up and spin down? As you can see in this experiment, here is shown resistivity of nickel doped with 1% of different materials, and this measurement at 4.2 Kelvin. So you see they were doping it with titanium, vanadium, chromium, manganese, iron, cobalt. And then when you dope it, they performed measurements for resistivity for one and for opposite spin polarity. And you see that they are different. This is the first message. And principally, it can be larger or smaller than, so let's say for resistivity for spin up can be smaller than for spin down, like here, or vice versa. It can be higher for spin up and spin down, because different mechanisms can contribute to this, which we'll discuss. And the largest difference in the resistivities for cobalt is 20 times. Yeah, so here, these 2 points. Why is it happening? So first of all, if you want to have a conductor, you need to be sure that you have electrons to conduct your energy. So in this band model, it means that at Fermi level, you have enough electrons. But if you make one step more in the direction of a real material, for example, some ferromagnet, like it's shown here, in Stoner model, we have seen that this particular 3D band of electrons, due to exchange interactions, they are shifted. That's why you have different density of electrons at the Fermi level for a spin down and for spin up. But in this case, you should ask you, and it looks like here you would expect conductivity to be larger because you have simply more electrons. And nevertheless, in this case, you should ask which electrons are actually responsible for the conductivity in your material. And in reality, conductivity in this kind of materials is mainly given by the s electrons. You see this band, they don't have so large density of electrons in the Fermi energy, but the band is broad, much broader than D band, and also effective mass, which can be found as 1 over second derivative of the dispersion curve. So this is something we do not go now, but electrons in this conductivity, you need to take into account not real mass of electron, but effective mass of electron. And for S electrons are usually heavier. So it means that electric conductivity then is mainly given by S electrons. And now we are coming to question not what is carrying your electric charge, but what is scattering this electric charge. And these S electrons are scattered on D electrons. It means that in this case, this particular case, like it's shown here, your spin down electrons, since there are so many D electrons, 3D electrons, these S electrons will be more efficiently scattered. It means that resistivity for these electrons will be high, and spin up electrons will be better. Conductivity is better. That's why you see this resistor is larger, assuming that here resistance is large, and this one is better, so this is smaller, so it means it's better conductor. Okay, so this is a bit about two-spin channel model. And as I said, one of the assumption we made here that there is no spin flip scattering. Spin flip scattering, it's a scattering when your electron is propagated, reaching some impurities of phonon, and after scattering, it flips the spin. Two spin channel model doesn't work in this case, and in some materials we cannot use it, but in some materials it works perfectly. Therefore, we just need to know a bit where to expect to have spin flip, and that's why I will make now a little detour to speak a bit about it. So first, what we need to understand about spin flip scattering is that when you, so it's such as scattering at which spin orientation of the conducting electron changes from up to down or vice versa. And what we need to take into account that to conserve the total spin, the spin of the scattering center or impurity must also change by Planck constant. So you have spin half Planck constant, also half Planck constant. So it means that when you change the scattering, you have to give somewhere this momentum in order to conserve it. And the integration book it defines three different directions where it can happen. So one way is when the conduction electron is scattered by a weakly coupled magnetic impurity. And then you change the spins of the magnetic impurity itself. In second case, the conducting electrons can be scattered by spin waves or magnons, which are quasi-particles with spin 1 as a truth. Also, yeah, so of course, magnon it is already. So if you have electron up and then you split and move it down, it's already a magnon. Therefore, it's right. You can have this scattering, like it's shown here, spin up and spin down, when you will generate one magnon. And third one is scattering by impurities with strong spin orbit coupling, such as gold, for example. And then spin orbit is responsible for spin flip scatterings usually. And this is very important. That's why now we will speak about spin orbit interaction, because in modern magnetism, in modern spintronics, a spin orbit is very important. Maybe the most important parameter. In some cases, it can be ignored, but nowadays it's so it's kind of second the order of smallest. But nowadays, technology came to such systems and to such sizes that spin orbit interaction plays a very important role. And therefore, I want to say a few more words about it. So we discussed in the previous lectures that magnetic moment of atom in the simplest Bohr model of atom is given by two contributions, by spin of electrons itself and by orbital motion, and by orbit of electron, L and S. And principally, we consider that they are independent. So the total angular momentum of your electron, it was simply a sum of L plus S. Nevertheless, in some materials, they are dependent. So spin of electron is related to the orbit. How to describe it? The simplest way how you can find it in this book, you do the following. So this is your original atomic model. You have here in core, you have Z protons. That's why the charge of electron is Ze. This is simply atomic number. And then what you assume that radius is inversely proportional to the Z. So the more protons you have, the closer your electron is rotating. Then you're making a mathematical trick. What you say is that, okay, now instead of electron moving around the nucleus, like this is Sun, this is Earth, you do that what people believed for quite some time, that Earth is staying in the middle and is not moving, but Sun is moving around. So you come to, basically it means that you are coming to a new system of coordinates, which is moving together with your electron. And then in this new system of coordinates, your electron is not moving, but instead we have a proton, so nucleus, flying around with the same radius. And then following exactly the same steps which you did at first, I think, our lecture, you can clarify that there will be this motion of nucleus will create such current with positive charge, because it's positively charged, with this Z, which tells you how many elementary charges you have in the system. And it will create a magnetic field at the point where electron is, which can be found in this way. Good. And then what we can say, how our electron will feel this magnetic field from nucleus. Since it's not moving in our new coordinate system, system of coordinates, you can forget about orbital motion. But your spin, if your electron has spin up or down, will feel this magnetic field. And then what you can do, and the magnetic moment of the spin, as we discussed already, can be found in this form. And then interaction energy, it's just scalar product minus scalar product of magnetic moment with applied magnetic field and all magnetic inductance. You will get interaction energy of spin orbit interaction. And as you see, what's very important here is that it's proportional to the product, scalar product of orbital momentum with spin momentum. So it means that if you will take materials with zero orbital momentum, like for example, we were discussing yttrium iron garnet, so some garnet material with iron 3+, it has electrons, the 3D states, they all your orbital is half filled exactly. So you have only electrons with the same spin orientation. So if you summarize orbital momentum, it will be -2, -1, 0, 1, 2. And it means the total orbital momentum is 0. Then in this case, if your L is equal 0, you do not have spin orbit interaction, in ideal case. And S cannot be 0, so it's always plus minus 1 or 2. And projections to Z axis. And second important result we are getting from here is this one, Z to the power of 4. That it's atomic number, so we see that atomic number is very important, and it's that what we expect in the experiment, that only heavy materials, heavy metals, have strong spin orbit interaction. So very typical materials which we are using in experiments when we want to have strong spin orbit interactions could be platinum, tantal, tungsten, gold, but gold, yeah, it's slightly different compared to this one. Palladium. So this kind of materials are usually used in experiments because as we see, spin orbit interaction is proportional to that to the power of 4, and it means that we should expect it more pronounced for heavy metals. Few more words of what else we have from spin orbit interaction. You can see it in the spectroscopy, because now energy levels of your electrons, so this is energy given by the principal quantum number n, but you can add this additional energy contributions which we just have found. And since you can have only 2 states, spin up or spin down, it means that there will be 2 additional states when J is equal L plus 1/2 and J is equal L minus 1/2. Of course, if L is equal 0, so these are s orbitals, as we discussed. If L is equal 0, there will be spin orbit interaction will be 0. That's why in all these s orbitals, you still have even with, so you simply do not have spin orbit interaction for them, and it still stays the same state. But if you go to larger L, then you see the splitting of energy levels into two, here and here. So this is a result of spin orbit interaction, and the only last point which you just have to keep in mind that in spectroscopy you cannot usually see all of this spectra, because what you measure in the spectroscopy is a energy difference between them two, between the layers. So you just will get new spectral lines at different energy points, and here you need to have, since it's a question of technique, yeah. So you will put additional selection rules onto your scattering. That's what you can see. For example, that you need scattering with a change in the orbital momentum. So it means that you do not scatter in line, but you scatter from L equal 1 to L equal 0, like this, or vice versa. Also, you have some condition on this projection of this quantum number, projection of orbital momentum, but also you have to change total angular momentum must play plus minus 1, so like from 3,2 to 1,2, like this one. And this is what we have, such scattering. And yeah, the last point here is you can see in the captions that although it's allowed to have scattering that with change in total angular momentum 0, like it's shown here, from 3,2 to 3,2, but in experiment it's very weak. Therefore, it's shown here with dashed line. Good. And last slide is where do we see this spin orbit interaction? So we have seen already that it's when you do spectroscopy of a material, spin orbit interaction matters. But as I said, now it's the core of all spintronics. So if you will, we will discuss, for example, spin Hall effect. We will discuss some spin transistor, quantum spin Hall effect, topological insulators, Majorana fermions. That's all we will not discuss, but this is something very hot nowadays in modern physics, direct materials, called atom systems, chiral Magnonics, or chiral spin wave physics, spin orbit torque phenomena, which we'll discuss, spin transit torque, spin Hall effect, spin Zerbeck effect. So all these modern large research directions, they all require spin orbit interactions. But besides, as we discussed already, we talked already about spin orbit interaction when we were briefly mentioning crystallographic anisotropy, because orbit is something which is related to your lattice. Therefore, if you change orientation of magnetization and lattice stays the same, if you see that something different for this magnetic field and for this orientation of magnetic field, you need to expect that spin orbit interaction is here, because magnetic response is given usually by spin, and it doesn't care where your orbit is. But crystallography is always coupled to the orbital of your electron. Yeah, therefore, if you see that you change magnetic orientation or magnetization orientation of your sample and something changes, then definitely you have crystallographic anisotropy, and it's coming from spin orbit interaction. The same was about magnetostriction. Also, we need a spin orbit interaction. Okay, so now we have knowledge about two-spin channel model, and we are ready to switch to the next lecture devoted to spin polarization and half metals.